Okay, thank you so much, Johan. And we're really happy to be here. And so thank you all for having us. Before we get started with the workshop, we have some interactive portions of the workshop so that everyone can participate. And so before we really get started, we need to make sure that everyone is on the same page with computing. So we'll take around 10 or 15 minutes this morning just to make sure that everyone has everything that they need installed to be able to participate today. So first things first, all of our materials are available online. And Johan, I don't know if you've emailed them the link. Okay, so you all have this link, but in case it's not handy, the link is restorts.github.io/record-linkage-tutorial. And so this has all of the materials that you'll need for the entire day, including slides, code, and then kind of some objectives for the day. So once you navigate to this website, there is a table here with all of the topics that we're going to cover. The first topic is setup, so that's where we are right now. So first things first, I want to make sure that everyone has R installed on their computer. So if you don't have R installed on your computer, no shame, but if you could just raise your hand so that we know how many need to get set up. Okay, so we've got one need to get set up on R. Okay, so installing R, it's fairly straightforward. So within the deck, there's a link here to the R project and some instructions on how to download R from CRAN. And then it's simply following the instructions from R to how to install R. So I will come by later and make sure that you're set up with R, but we can move on then to the next step, which is to install RStudio. And this is an optional step. If you are already using R and you do not want to use RStudio, that's perfectly fine. You don't need it for the workshop, but I will be using RStudio, and so I want to give you the option to install RStudio if you like. So I like RStudio because it's a nice IDE, gives you the ability to see code, does syntax highlighting, gives you auto-completion as well. So a little bit of plug there for RStudio. It's really nice. But I understand that people have their own working environment, so you do not need to install RStudio. But if you would like to, now's the time to do that. So there's some instructions on installing RStudio here. Again, this is fairly simple. Go to the link and click download for the open source, which is the free version, and then follow the instructions. So feel free to do that now. Okay. The last part of our setup is to simply install some packages that we're going to be using today. So I have on the website, I have a set of just, and I've already actually, so this is simply our script to install all packages that we will need today. They're fairly simple, and we will actually discuss kind of the purpose of each of these packages as we need them. So really right now, I just want you to be able to run this script and get the packages that we will need. So I'll go ahead and run it with you. So I'm in RStudio, so in order to run this line, I am on the font and I hit Command, Control, Enter, and it runs that line. It starts installing all of these packages. And take a few minutes. Yes. Wi-Fi? Okay, great. Any other questions? It's okay if there are. Yes. One package? Which package? iGraph. Okay. Let me come by and have a look at that. Is anyone else having trouble with iGraph? Okay. So while this is installing, just install both lines. The second line depends on the first line, so don't try to run it first. Go in order. And then take minutes, and we'll check back in to make sure that everyone is set up. Make sure that everything's set up for you. We'll have a break in like 45 minutes. Okay, so I can run now the second line, which just installs a data package, and this should be faster. Hopefully. Anybody else have any installation issues? Everyone's good to go? Okay, great. Then that should be our setup.
It's closed, Johan.
Okay.
Can you hear me okay?
Yes, yes.
Okay, great. So I just want to thank Johan and CMAT and Nehi for inviting us to give this workshop. This has been a really great experience for us to put this together, and I hope it will be very useful. I'm very upset that I'm not there in person, but I'm glad that we were able to work out a situation such that I can give this presentation to you all remotely. And I just want to thank Johan and everyone for allowing this to happen. I just want to quickly thank Andy and Brenda and Betty for working on this in a really collaborative way. So I hope your interactions will be really positive with them. They've worked really hard on this. So the first part of the workshop, I'm going to do a very high-level overview of entity resolution, what it is. I won't make any assumptions that you know what I'm talking about. And a lot of the work that we've been doing has been heavily influenced by work done by the Human Rights Data Analysis Group out of San Francisco, and also some recent work that I've been doing with the U.S. Census Bureau, where I'm working part-time. So I first just want to start out by explaining what is entity resolution. This is also known as record linkage or deduplication, and it's the process of joining multiple data sets to remove duplicate entities that's often in the absence of a unique identifier. And so I'm going to start with some motivating examples of how I've thought about this. And you'll see these carry throughout the workshop. And the one I did, at least myself, and also some of the others in the group, such as Betty Chen and also Brenda and Andy, is in the current ongoing conflict in Syria, there's this duplicated information regarding individuals who have died in the conflict. And a motivating question is how would you estimate the documented the number of documented identifiable number of deaths and some sort of associated standard error of this. And so Betty and I will talk about this later in the day regarding some new methodology and what we call unique entity estimation for tackling this problem. But you could easily then ask the same question about, for example, the US Census or the Mexican Census. So in the US Census, we get duplicated information of individuals that are filling out the decennial census every 10 years. And so then when you're wanting to try and understand the accuracy, for example, of the decennial census with maybe looking at this with the post-enumeration survey, this is a very timely and important question. And so these are just two motivational examples. There's many more going into the medical literature, industrial applications, and so record linkage or entity resolution is becoming it's becoming a very important, timely problem, especially as a society we collect more and more data. So what does an entity resolution problem look like just from a simplistic westernized example, well, if I think about just 3 arbitrary data sets, well, I'm going to look at these data sets as a graph with no edges. And the data sets I'm going to look at, I'm going to call them Apple, Amazon, and Google. And I'm going to assume that each data set has entities within them that are duplicated. So you can have duplication within a data set and across data sets. And each entity is represented here as a node. So for example, Larry Wasserman, he's a person, he's a professor at Carnegie Mellon, and he's a particular entity in this data set. And there's other underlying information associated about Larry Wasserman. So what does this information look like? Well, more before we look at Larry Wasserman's information, we're wanting to try and understand who's who in this example, in the record linkage problem. So if the purple Steve Feinberg is the same as the red Steve Feinberg, then we're going to want to put an edge. And if they're not the same person, then we're going to remove that edge. So how do we do that? Well, we look at this underlying information behind Larry Wasserman. And so if we look at some underlying information that we have about him, well, if I just look on the white pages, publicly available information, then I learned that Larry Wasserman has an address. He lives in Pittsburgh, Pennsylvania with a zip code, and he has a particular phone number. And so by using this textual information, I can associate whether Larry Wasserman is the same as another Larry Wasserman or different from, for example, Stanley Wasserman. And then I can play the same type of game with the different Steve Feinbergs. So with the purple Steve Feinberg, I can try and understand if it's the same as the red Steve Feinberg. And then I can do the same type of thing with the other Steve Feinbergs. So just to drive the point home a little bit further, if you notice what's happening with the Steve Feinberg, E and the I are flipped. And if I look into these two Steve Feinbergs a little bit further, then again, using publicly available information on the white pages, I have a Steve Feinberg that lives in Pittsburgh, Pennsylvania at a particular address with an age range of 50 to 54 and a phone number. And then if I look at the Steve Feinberg with the I and the E flipped, then I get a different address. I get a top-coded age and a different phone number. And so if we just look at this using, the textual visual information, then these are clearly not the same Steve Feinberg. And so looking at this manually is called hand matching. This is typically done in terms of trying to understand whether a record 1 on the left and record 2 on the right are the same person. And so this might be used as some training data. And of course, this is expensive to curate. So what we're wanting to do is come up with sound, automated methods that will come up with whether these two Steve Feinbergs are the same or not. So now I'd like to turn to what this looks like for the Syrian conflict. So it looks exactly the same as the westernized example, except now the nodes are in Syrian Arabic. I have information associated with each particular entity, so with each Syrian name. So with each Syrian name, I can extract textual information about each entity. And so I have information that's a bit different, but it's quite similar. So I have a date of death for each person. I have the location where the person died. I have the gender, and I have other information. And so when we get into a few more lectures ahead, we'll go into this example in more detail. So one of the questions that's asked a lot is why is record linkage or entity resolution so intrinsically difficult? So this problem was discovered and written down formally in the late 50s, early 60s, but significant progress wasn't really made until recently. And so why is that the case? So there's 2 reasons for this, and it has to do with 2 competing reasons. So if we suppose we have a total of M records and D data sets, then what we seek models that are much less than quadratic. So we're wanting models that are much less than big O of M squared. But we're also seeking models that are reliable, that are accurate, they fit the data well, so they're robust, they're not sensitive to hyperparameters or any tuning parameters. And we also want models that account for the uncertainty of the model. And so if we think about this, these two goals fundamentally go against one another. And so they're making this entity resolution problem very challenging, because we're wanting 1 and 2, and these fundamentally go against each other. So how can we have 1 and 2? Well, there's only a few papers I know of that actually satisfy 1 and 2. And so we'll talk about a paper that Betty and I have recently worked on that actually satisfy 1 and 2. But typically, depending on the motivating goal of a record linkage task, we'll need to approach it using either 1 or 2. And approaching it using both is incredibly challenging. So just to turn a little bit to some terminology, you don't have to think about the record linkage task as duplication within or across in terms of the whole space that I was talking about. So a lot of people will talk about a subtask of record linkage, which is known as deduplication. And so again, this is a subtask of record linkage because it's breaking the space down and making some restrictions about it. And this is quite common. So it's a computational tool that's used. And then another computational tool that's used is called blocking. And so Brenda will give an introduction to this and go into it in more detail. And then Andy will go into this in great more depth, talking about computational speedups and advancements that have been made in blocking. So if I think about deduplication, what I'm doing is I'm taking these 3 different databases, but it could be an arbitrary number of them. It could be K. And I'm cramming all of the data together. So what am I giving up here? Well, I'm giving up the fact that I can no longer propagate the uncertainty of the record linkage process exactly. So that's what I'm giving up. And what am I gaining? Well, I'm gaining a lot of computational tractability because I no longer have to search this entire graphical space. So a great deal of the literature can be grouped into the case of deduplication. And so many examples that span both academia and industry are these semi-supervised cases such as logistic regression, random forest, support vector machines, Bayesian adaptive regression trees, locality-sensitive hashing, and you could keep going on, many clustering methods, such as Dirichlet processes of that nature. But when you start looking at a Bayesian methodology that's looking at the record linkage process, looking at all of the data sets and the records, the duplication within and across, then you're not looking at deduplication anymore, but you're looking at the record linkage process of the entire space. And so there you're actually able to propagate the error exactly. And so in the last module of the workshop, Brenda and Andy will talk about this more and the strengths of tackling things from this approach. So again, this is the record linkage graph where you're looking at record linkage, within each. You assume you have record linkage within each database and across each database. And so I'm referring to this as record linkage here, since we can actually propagate this record linkage uncertainty of the entire graphical structure. So as an example, you could look at this entire uncertainty of the record linkage process and look at the capture-recapture process afterwards, for example, for a census or for something like the Syrian conflict or for any application. You could do something much more simple, like just looking at a logistic regression. So now let's turn to blocking. So what is blocking? So blocking, again, is it's useful for this fact that when you look at record linkage, and suppose you're looking at it just for 2 different data sets, then if I think about this red space right here, then if I do all-to-all record comparisons, then that comparison that I'm doing for m total records is going to be of the order of records. It's going to be quadratic. So if I think about this red space I'm showing you, then each comparison is like a pixel on the screen. And this red space I'm showing you means that I'm having to do all-to-all record comparisons, and that's not computationally tractable. So the red here means that, we can do better than this. This is bad. And what we can do instead is we can perform some blocking, or rather partitioning, where we partition the records into some maybe similarity metric, where we put similar records into partitions, such as the red partitions or bins, and that's where we do the similarity comparisons. And then the green space is where we get our computational savings, and we never have to search there. So of course the question is, well, what's the right way to do blocking? So how do we do blocking in a sound way that's computationally fast? And so Brenda's going to go into blocking in more detail because, again, this is a complicated issue. And then Andy will go into more sophisticated techniques and show these to you later. I'll review just two of these very briefly. The most common method used for blocking is this deterministic method of blocking. So a deterministic method is saying that, well, suppose my data set contains name, first name, last name, gender, and date of birth. And maybe I think that for the particular data set I'm using, I strongly believe that gender has very little error in it. Then what I can do is I can partition on gender and treat that as error-free or fixed. And then I can block or partition on gender. And so what that does is it treats gender as a block, and I get a computational savings on that. And then one could imagine that maybe also you believe date of birth year is also quite error-free. So then you can also imagine doing a blocking scenario on both gender and date of birth year. So what is the downside? Well, you're treating, for example, gender as being error-free. And this isn't realistic. So you're not able to propagate the error from your blocking procedure. And so you don't know what errors you're making. The upside is the fact that you're able to do something computationally very fast, and the speed ups are quite easy to measure. The second type of blocking that's more widely used now are these types of probabilistic blocking. So an example of one that I'm a big fan of and I promote a lot is locality-sensitive hashing. And so we'll spend quite a deal of time talking about this, talking about what locality-sensitive hashing is, why it's useful, and specifically why you can embed this in a record linkage procedure. And so Andy will specifically talk about locality-sensitive hashing, and Betty and I will talk about how you can actually use this for record linkage in a sub-quadratic fashion. For a review on blocking, Peter Christian has a fantastic book on just record linkage and blocking in general. And then I have a paper with Sam Ventura and Mauricio Steenle and Steve Feinberg in Privacy and Statistical Databases that does a survey of blocking. And then Betty Chen and Anshu Shrestha and I have a paper that's now in minor revision that uses a variant of locality-sensitive hashing, using it for what we call unique entity estimation that Betty and I will talk about. And we have software for this. We'll talk about this in one of the later lectures. So let's turn now to some common methods for entity resolution. So I already mentioned that you can match. I already mentioned that if you have, for example, the two records of Steve Feinberg, you could perform what's called exact matching. So exact matching, this would be, let me just go back. So suppose I have these two records of Steve Feinberg. Well, exact matching here would be, I would be comparing all of these records on every feature And if every feature exactly matches, then I would say that these two records are a match, and otherwise I would call them a non-match. And so you can hopefully imagine the issues with exact matching. But this method is heavily used in sociology, political science, and a lot of the social science venues. Of course, if you have a unique identifier and you know that it's known to be very sound, then you can simply just use the unique identifier such for record linkage. We know that from looking at real data, it's often not the case that you have a unique identifier in practice, or that you may have a unique identifier that is quite noisy. And so typically, a unique identifier can't be used in practice. So the first method that was used for record linkage was written down by a geneticist, Newcomb, and then Follagy and Sunter in 1969. It was this very simple idea, but the whole idea was simply just looking at a likelihood ratio test or a hypothesis test. And so if you look at the likelihood ratio of these two records, and it exceeds a certain threshold, call it T, then you say that the two records are a match, and otherwise you call them a non-match. And so what's the problem with this method? Well, one problem is the fact that the threshold is very sensitive. So how do you choose the choice of the threshold? If you don't have any training data, then there's no way to choose this threshold. And so this is very problematic, for example, in something like the Syrian data set or census applications. Another big issue is transitivity. So transitivity is where, suppose you have a record 1, and record 1 is connected to record 2, and record 2 is connected to 3. Typically, you want to connect that link from 3 to 1. Well, under hypothesis testing, there are many different ways that you could try and impose transitivity. However, it's not clear what the optimal one is. So there was a paper that actually addressed this. And so the paper was written by a really excellent student of Steve Feinberg's, Mauricio Sedinle, who's now at the University of Washington. And so this paper, which appeared in 2013 in JASA, so what Mauricio showed was that you can look at k different databases and extend the Follagy-Sunter method and look at all variants of k-tuple hypothesis testing and actually impose transitivity. However, the issue here is that because you're having to look at all variants of k-tuples for the hypothesis testing, things become intractable for more than 3 databases. And so this kind of just shows another issue where the Follagy-Sunter method, it's not really intrinsically built in a natural framework for record linkage. And so in my opinion, it's a major flaw. So another important point, and this will we'll talk about this a lot in the workshop, is, well, how do we evaluate the performance of a particular record linkage method? So I'll define these in just a moment, but one important notion is the idea of recall and precision. There's this other notion of the reduction ratio. So the reduction ratio is, I talked about computational tractability. So we want to know if we start with the entire O of m squared space, how much can we reduce that space down by some sort of blocking technique? We typically want to look at an estimated sample size. And then, of course, we want to know a standard error of this. We also would like to know, does the runtime match the computational complexity of our algorithm? We also want to know the robustness any tuning parameters. We want to do a full sensitivity analysis, make sure that things are reproducible and fair. And then finally, something that at least I worry about, I always worry about, do supervised methods or semi-supervised methods overfit the data? So what I mean here is you need to be very cautious that you're not, if you're using a semi-supervised method, you need to be very cautious that you're not giving it too much data. So I'll show an example of this in just a minute. So I'm just going to quickly review some evaluation metrics. So we'll start with some definitions. If we have pairs of data that can be linked in both the hand-matched training data, so we'll refer to this as the truth, and under the estimated linked data, then we'll refer to the situation as the true positives. And then if we have pairs of data that can be linked under the truth but not linked under the estimate, we're going to call these false negatives. If we have pairs of data that cannot be linked under the truth but linked under the estimate, we'll call these false positives. And then pairs of data that cannot be linked under the truth and also not be linked under the estimate, we'll refer to these as true negatives. And so from this, we can define the recall as the number of true positives divided by the true positives plus false negatives. So you can show that this is equal to 1 minus the false negative rate. So you want the false negative rate to be very close to 0, and you want the recall to be very close to 1. So similarly, the precision then is equal to the true positives divided by the true positives plus the false positives. So you can show that this is equal to 1 minus the false positive rate. And so again, you want the precision to be very close to 1, and you want the false positive rate to be very close to 0. I'm not going to formally define the reduction ratio because it's a lot of notation. For details, you can look in Peter Christian's book, or you can look at the 2014 PSD paper. But the general idea is it's just measuring the relative reduction of the comparison space from, for example, a deduplication technique, a hashing technique, or a blocking technique. And so you're wanting that space to be reduced in terms of a percentage as much as possible. So the other evaluation metrics that I talked about were the estimated sample size, the standard error of the estimated sample size, the runtime, the robustness to the tuning parameters, and then do supervised methods overfit the data. So of course, the estimated sample size and the standard error must be defined for each method. But as we'll see, this is not difficult to do in practice. If we turn to 2, any method can be evaluated also. So this is turning to 3. Any method can also be evaluated also for the runtime. So you can gauge your computational costs accordingly. And you can also see if they're matching up the computational complexity, which you could derive for a particular method. In terms of robustness of the tuning parameters, this should be explored from a Bayesian perspective, a frequentist perspective, whatever type of modeling approach you're looking at. And one thing again that I like to hammer on is it's very essential to make sure that supervised or semi-supervised methods are not overfitting the data. So for details on this, I have a paper from 2015, and I'm going to talk about this a bit in detail about why this is important. So to look at an example on data that's available from the record linkage package in R. And what I'm going to do is I'm going to compare many different methods according to evaluation metrics that I'm going to lay out. So I'm first going to describe the data set and compare the following methods in R. So in this 2015 paper that I worked on, I developed, from the methodology, I wrote a package that's in R or CRAN called Blink. And Andy's going to walk through a demo of it at the end of the workshop. I'm going to compare it to logistic regression, random forest, adaptive regression trees. So I'm just going to give you kind of a short flavor of the data set and some summary statistics of what it does. So the RL Data 500 data set, what you have is you have first and last German name, and you have full date of birth. and that's it. So the data set is quite small. There's 500 records and there's 10% duplication. So it's very sparse in terms of the amount of duplication. So what we do here is I build a generative Bayesian model. I'm not going to show you the model, but Brenda and Andy will lay it out for you later. And what you do here is what you get out of this model is you get a posterior density for n, which is the estimated sample size from the simulation. And you can also sort then from there, since you have unique identities, you can look at the false negative rate and the false positive rate. So here on the left is I'm looking at the estimated posterior, and then the black line is the true number of people in the population or sample, which is 450. And then the red line is the estimated. And you can see that it's quite close. The estimated posterior mean is it's almost on top of the truth. And you can see the FNR and FPR are quite close to zero. On the right-hand side, all I'm looking at here is a mathematical construction of this particular study. And the black nodes are the pairs of records it's getting correct. The little dots are the singleton clusters. And then the red one is the one that it got wrong. So it mislabeled one false positive set. So this is kind of just showing you the flexibility of the Bayesian methodology and what it's giving you. You can also see that things are transitive here inherently. So we can also do these very nice comparisons just in terms of FNR and FDR. So if I look at Blink, I can look at FNR and FDR. I can compare to exact matching, or I can compare to near twin matching. So near twin matching is, I say two records are going to be the same if they disagree at most by two features. So that would be two textual fields. And then I can look at it, I can compare to Bayesian adaptive regression trees, random forest, and logistic regression. So for these, what I did is I fed it different amounts of training data. So I gave it 10%, 20%, and 50%. And so here I wanted to see how the error rates changed by giving it different amounts of training data. And you can see they changed pretty dramatically. And so I think that's why I have this concern of you should be very careful with things like record linkage and how much training data you're giving a semi-supervised method compared to an unsupervised method. And especially doing such comparisons as these. And so I'm happy to talk more about this if there's questions. So I mean, you can see if you give it the full data, then of course it does better. And of course, if you think about the unsupervised approach, you're not giving it any data at all. So the unsupervised approach of Blink is already an unfair comparison. So I'd like to now turn to robustness. So how do we make sure a method is robust? So for a semi-supervised method, we want to make sure it's robust to different choices of the training and test data, and also any tuning parameters. So for probabilistic and Bayesian methods, we want to make sure these methods are robust to choices of the hyperparameters and tuning parameters. So you need to sweep through every single choice of the tuning parameter and make sure that the posterior isn't sensitive to those. And that can be quite difficult in practice. So if we're looking at robustness, computational time complexity, and full sensitivity analysis, I explore these a lot in this paper that I wrote in 2015 about pros and cons of the methodology that I worked on. And then also furthermore in a paper that recently appeared in JASA with Rob Hall and Steve Fein. So one thing I've thought about more recently is record linkage is becoming more of a field that people are working on. It's something that's very important in terms of applications. And so I wanted to spend a bit of time talking about what we need as a field and a community, especially at an international level. So I think the first thing, this is hitting on really well because this is what we're doing. We need more workshops and forums. We need more discussions, especially more interdisciplinary communications about, between official statistics organizations, industry, and academia about what we can do to press things forward. The second thing I think is really important as well, we need more open source software so we can do things like 3 reproducibility, fairness, and then moving to 4 evaluation metrics and comparisons. It's very difficult to understand what methodology one should apply, for example, to the decennial census in 2020 when there's very few pieces of software that are openly available. I think it's also really important that methods are transparent about what they do and what they don't do. And then something I've been thinking about for the past few years is, well, if you think about what record linkage is doing, it's doing something that's hopefully should be quite alarming to you. So it's uniquely identifying who people are. And you can uniquely identify who people are, even using data that has been anonymized, and this is not new to us. So how can we think about more ethical use of data? What are proper privacy protections of sensitive data? How should we think about this so that we're doing things in a sound way with privacy protections? Can we actually do record linkage in more privacy preserving ways? And so I think it's important to have more conversations with record linkage and the privacy community. So some papers and books I wanted to touch on and just kind of note things that have been really useful, at least to me and my group. Peter Christian has had a huge influence on my work. His book and so many of his papers. So he does a lot of really nice comparisons, and he's very thorough. So I've tried to replicate this a lot in my own work and tried to impress this on students and postdocs that are coming through my group. Mauricio Sedinle does a lot of really fair comparisons as well, so I'd urge you to look at his work too. If I turn to the record linkage and privacy literature, one of my favorite papers is led by one of Peter's former postdocs, Danusha Vatsalatin. And it's just a really great paper on privacy preserving record linkage and what types of evaluations you should use. When I think about reproducibility and fairness, there aren't any specific papers on this in record linkage that are aimed at reproducibility and fairness. But when I think of reproducibility, I immediately think of Victoria Stodden, and just from conversations with David Dunson, I immediately think of a lot of his work. It's always reproducible, and he thinks about fairness in a way that I think is very important. So Betty and I will talk more about this work that we've done with the Syrian data set, where we've tried to make everything reproducible. We've tried to do comparisons that are as fair as possible to the existing literature and also with the evaluations. So we can say more about that when we get to that section. And then finally, a huge inspiration has been from the Human Rights Data Analysis Group in terms of their ethical use of data, pushing forward, things with human rights. And so this has been largely inspired by a lot of work by, David Banks, Megan Price, Patrick Ball, Anita Gomez. So if you're not familiar with their work, I would encourage you to read it. It's really amazing. They're a small nonprofit group. So I think those are just some key papers that I would point you to. So where are we headed for the rest of the day? So I just finished this introduction to entity resolution. And next, Brenda will talk about an introduction to blocking with some demos. And then Andy will talk about an introduction to locality-sensitive hashing with some demos. And then Betty and I will talk about unique entity estimation applied to the Syrian conflict. There's software available. It's in Python and C++. So if you're interested in the software, feel free to talk to Betty. I'll also be online, so feel free to talk to me about it. And then finally, we'll end the day with some Bayesian approaches to graphical entity resolution. And this will be done by Brenda and Andy. And again, there'll be some demos here. So finally, I'd just like to take any questions and thank you for your time.
Are there any questions, comments? Sí, si tienen preguntas en español. ¿Comentarios? No. There are no questions here.
Okay.
So, thanks. And you are the director of... Okay. Yes. Okay. Yes. Okay, so we will have a small break. Let's take 10 minutes to make it more smooth. Yes. And in the meanwhile, we'll switch the computers here. But before we leave, well, although we are on a distance far away from North Carolina, on behalf of everybody here, Rebecca, thanks a lot. We will hear you again in the afternoon, but an applause.